Hi, my name is Zhong Hong Lin, and now I'm an associate professor in National China University in Taiwan. So first, I would like to thank the invitation, and I'm happy to share our recent results, which we developed the cell power the sensors based on the thermometry and the thermometry the effects. So let's talk about the motivation. So actually, we all know that the global wearable market is coming. So you can see that for the device the shipments in the 2012, we can expect it's more than the 190 millions, and actually the market is around the 48 billion by the 2023. So of course it's very big. As you can see that many of the wearable devices has been used to collect the information from your bodies. However, if all the data actually there is no purpose to build the connection between some specific disease. Then it's just useless data. But however, if you can find some connection, actually even you didn't develop the new wearable devices, but you can also find some new applications. Okay, for example, nowadays, no matter for the healthy people or for the patients, actually we always wear the medical devices and to collect the data and then send to the cloud, and then we can also develop the algorithm, right, to analyze those data, and finally the analysis the result can use for the medical doctor to predict if you need further the medical treatment or not. So some company they already developed the commercial wearable non-invasive or minimally invasive the biosensors. For example, the most famous case is the Google. They want to integrate sensor into a contact lens, and they use the electrochemical way to detect the glucose in your tears. Yeah, so many companies have developed similar the technologies. Or you can see this is a paper published from the Professor Ali Jabi's group. So you can see that they try to detect some smaller biomarkers as well as the heavy metal ions or the normal metal ions in your sweat samples. So those are very convinced that now the wearable devices, many people want to use that for further medical applications. However, even they are it seems that they are really good, but they always has the problem of the battery or the show of the power. So actually some company like the Revlon or the Tommy, they already try to integrate the solar panel into their products like the jackets. And anyway, it's not cheap. So in our lab, we also want to develop such kind of useful technologies, but we focus more on the biomedical and the thermal energies, because these two kinds of energy, they will not affected by the environmental the factors. So it's all and can be generated from our own bodies. So first, when we talk about biomedical energy harvesting, of course, it was seen about electromagnetic generator, but actually, because it's the operation principle, it will use the metal and magnet. So that means the device could be a little heavy, and they need to relatively to rotate. So that means the structure will be three-dimensional and rigid. So maybe this is not good for the power source for the wearable the sensor. Then in 2007, Professor Zhong Lin Wang, they decreased the size of the piezoelectric materials and developed piezoelectric nanogenerators. So this kind of device actually is good, like it can be the two-dimensional and the flexible. But the problem is that we all know that for the nanomaterial synthesis, how to achieve the large-scale production is always a concern. So in our lab, we focus more of the technology is the triple H nanogenerator, which is also proposed by Professor Zhonglin Wang in 2012. Its working principle is very simple. It's just based on triple H and electrostatic effect. And the most interesting thing is that all materials can be used to design this kind of the device, and they can also maintain the advantage of the two-dimensional and the flexible. So today I will introduce some results from our group. Okay, then first we need to talk about what is the triple H effect, or some people may call it a contact education. For example, we have done this when we were in the maybe the senior high school student. So you can see that when the two material contact, especially one material is better to be an insulator. Actually, the surface charges will transfer when two material contact, and we know that after the contact, actually the material can attract with each other. This is because of their surface, the electrostatic charges. But before the 2012, the Professor Zhonglin Wang proposed this device, this kind of device. Actually, we just feel the daily inconvenience from the triple H effect. So the triple electric effect now, in my opinion, or in many people's opinion, they will feel that this is an interesting science phenomenon, or they will develop the devices for the mechanical energy harvesting. But actually, from my opinion, it can be developed into many different kinds of devices for the different applications. So it has the infinity the possibilities. Yeah. So like today, I will show you some of our results. And then how this device work. So for example, you can just simply choose the two metal layer as the two electrode, and one electrode you can use as well as the contact material to contact with the PDMS. So because of the triple H effect, when they contact, actually the electron will transfer from the top gold electrode to the PDMS the surface, and after they separate, it will create potential difference, and now the electron will transfer from the bottom electrode to the top the gold electrode through the external circuit, and then reach a maxima. So because the triple H charges can remain on the surface for a long time, so once you try to push these two material to contact, now it's just like a parallel capacitor. So you will result in a decrease of the potential difference, and this time the electron will transfer from the top the gold electrode to the bottom the gold electrode, and then return to zero. So that means if you can periodically to let these two material to contact and separate, and it can provide you a continuous output. So many people just use this kind of device to collect the mechanical energy from the environment. Or some people, they will also use this device as a self-powered physical sensors, because for this kind of device you don't need a drive power, right, to let it work. So for example, if you observe the open circuit voltage, actually it can provide you the useful static information, for example regarding the deformation of the contact area. However, if you can observe the short circular current, actually the peak value will highly dependent on the dynamic process of the device operation. So that means you can collect more the information of the device. For example, some group have tried to develop this kind of device as the smart keyboards. For example, you and me, even we try to type the same word, actually the speed is different. But however, I feel this the kind of the devices more the possibilities because if you can modify the surface with some pro molecule, actually it can help to detect the target ions molecules or the microorganisms. So this is really, I think, it's really a new type of the cell-powered biochemical sensors because for the most of the traditional biochemical sensors, you will use the optical or the electrochemical waves. But for this kind of the devices, you just need the mechanical energy. Then it will give you a spontaneous output signal. So I think it's a new tool for cell power technologies. Improve the disadvantage of this kind of device. So you can see that this is the paper we published this year, a review article. So I work with the Professor Dr. Choi and the Professor Semin Lee. Actually, we have correct lots of the literatures regarding the solid and liquid contact education and their application for energy harvest and the cell power applications. Okay, also even on this kind of a device, it looks the fancy, but you still need to know there is something you need to know. For example, now actually we didn't systemly to compare the materials. For example, like how to design a molecule, which is good to be the triboelectric positive material or the negative material. So if your background is the chemist, it's very good to join this research area. Or if your background is physics, it's also good because most people now design these devices just based on electron transfer. But however, you need to know if the surface, your material surface, will also absorb some the water layer and can bring some the ions. Actually, during the contact education, the ion transfer will also happen. So how to find a balance between these two effects is also a good challenge. And if you are engineer, it's also very important. It's because, for example, in Taiwan, it's very hard to feel the humidity effect. The triboelectric effect is because the humidity is too high. So that means that the device, it will be highly affected by the environmental humidity. So you can see here, if the humidity increase from 10% to 50%, actually the surface charges will decrease by around 5 times. So that means how to pack this device and to avoid the effect from the environmental humidity is also a challenge. But this is also a big issue we need to overcome as soon as possible. So in a paper we published in 2018, actually we are very lucky to find if we change the contact material, we use the hydrogel as the contact material as well as the conductive electrode. Actually we can overcome the humidity problem. And because of this, the hydrogel itself is original like a solution. So we can also simply to coat on different kinds of the textile, for example, the sock or the t-shirt. Then we can develop the gap phase detector as well as the sweat sensors. And actually, the hydrogel we can also choose like the chitosan, and it also will bring the antibacterial function for the textile. But anyway, this is still based on solid contact education. So you can see that the hydrogel itself actually is not a good conductive material because its resistance is high. Normally will be in mega ohm range. But however, it still have some advantages. For example, it's a highly transparent material. And if you try to check the electrical property, you can see that it's very stable. For example, we simply coat the hydrogel on the commercial textile. no matter how we bend the test type, you will find the electrical property is still very stable. And of course, we also try and we found that is of course is the conductive, even if the resistance is high. So anyway, then we quickly to test how's the response output at a different humidity. So you can see that for the conventional, the TNG, if you use like the PTFE and the metal foil as the contact material, then you will find that once the environmental humidity is increased, actually the output will be decreased. Even the decreased level is just around the 20 to 30%, but it's still not good if you want to use this kind of device as a sensor. But however, if you change the metal foil, metal layer to be our hydrogel the layer, you will find that actually the output now can be maintained no matter how the environmental humidity changes. And this is because as the contact material, of course, the surface charge will be decreased once the environmental humidity increase. But however, the increase of the humidity will also bring the positive, the effect of the conductive, the increase. So that means it will compensate the negative effect from the surface charge the decrease. So this is the reason why our the design can maintain the output at a different humidity. And then we use this kind of the humidity resistant TNG to and integrate with the Kytosin based humidity resistor. So we can develop fully the cell power, the humidity sensing system. So you can see that once the environmental humidity is increased, the output goes through the Kytosin based humidity resistor will be decreased. And actually the signal change is much higher than if you just use the TNG as the humidity sensor. So we can even use the LED to replace the electrometer to develop fully the portable cell power humidity sensor. And you can just evaluate how many the LEDs are powered to calculate the humidity. So we also directly call the hydrogel to the commercial soap and to develop the gate phase the sensor. For example, we know this is very important for I mean that this can be used to monitor how you work. And now actually we are moving forward to the scoliosis and the bone fracture diagnosis. And you can, of course, you can also put this kind of device on the insole, so then it can become a smart insole, not only just on the commercial sock. Then the most difficult part for this project is that how to efficiently to analyze the signal and try to build up the connection with the disease. So this is what anyway, we hope we can show you the positive progress very soon. And then you can also just simply to use the power. Okay, this is the humidity resistant TNG as a power to drive like the wearable the electrochemical sensing system, or to generate some ROS and kill the bacteria on your clothes. So the output of the TNG we develop is around the 500 volt. Actually, it's not big. I know many of you are the experts, so actually you can develop much the higher output than me. But anyway, we just want to use the TNG and to store the generate electricity. So you can see that it can be successfully to store the generate electricity in a commercial capacitor. And then we just develop a small the cell power system after the generated electricity is stored in the capacitor, then you can just simply use a switch to release the stored electricity and try to drive the fiber-based electrochemical sensing sensors. So a lot of times usually we don't know how much electricity is needed for the fiber-based, the electrochemical sensor. So we just operate the device for 10 minutes and then we release the electricity. So that means that a lot of time if you work for 10 minutes, actually you can the stored electricity can drive the one-time detection to see that what's the glucose concentration in your weight, and the sensitivity can be further enhanced by coating the fiber surface with the platinum, the gold and the palladium nanoparticles. And then for the second story, actually we try to optimize how much electricity is needed to drive this the electrochemical sensing process. So finally we find that only the 30 seconds is enough. So it becomes very efficiently if when you walk or when you run. During the process, actually it can drive the many types of the sensing process and give you the multiple types of the sensing signal. And this time we change the target to the lactate. Anyway, the glucose and lactate they are very useful the biomarker in the sweat samples. And we also find that no matter bending or without bending, our system can still provide very reliable signal. Important is that this is a controllable property, so it's very different to like the silver based products, and it's controlled by your motions. So for example, for this project, we want to study the two different conditions. One is that your clothes is dried, so it's just like you only have the electric field effect or the electroporation effect. So you can see that for this study, actually we just put the electrode outside the solution. That means it will not contact with the solution. So if the bacteria will die, that will only because of the electric field. So you can see that we have tried the 3 different electric field, and for the highest the electric field, it can also result in a bacterial death, no matter it's the positive or the negative the bacteria. So and then for the other condition is that how about the textile is weight. So for this purpose, actually we further functionalize the textile with the nanowire in order to have the tip enhance the electric field effect. So you can see that the result is like when your textile, your clothes is wet, so it will also result in the electrochemical reduction of the oxygen and generate the hydrogen peroxide. And we all know now the hydrogen peroxide is not good for the bacteria. But of course, if its concentration too high, like more than the 100 micromolar, it will also not good for the normal cells. But however, the concentration generated by our motions, actually we can control, right? We can just control like below the 10 micromolar. So it will only result in the disinfection, but will not damage the normal cells. So this is very important. So you can see that once it's a high bar effect of the electroporation as well as the hydrogen disinfection, you can find that now the antibacterial performance is much better than the drier conditions. So we also design a system, right, just to store the electricity, and maybe before you enter your home or the office, you can just release the stored electricity and kill the bacteria on your clothes. Then you can very clean and safely to enter your home or the office. So that, of course, that we already demonstrate debate and demonstrate the humidity resistant TNG and their application. And the other option for humidity resistant TNG is we just directly use the solid liquid content education to develop the device. For example, in 2013, when I still was a postdoc in Professor Zhongli Wang's lab, actually I have mentioned solid liquid itself, like the water, can also contact with the solid and generate the triple charges. We have demonstrated that the hydrophobic or the superhydrophobic layer, and we very detailedly to study the mechanism. But the problem here is, okay, if your liquid is water, then you need to at least have the hydrophobic layer. So that will not be good for other sensing the application, especially maybe even the surface the property will not change too much regarding the hydrophobicity. And we also to use the solid liquid quantification to develop the ion sensor for the sweat detection. So you can see that we just also simply use the hydrogel as the conducting material and just to coat a hydrophobic PDMS layer. And once it contact the clothes absorb with the sweat, if there is the different ion concentration in the sweat, actually will result in a different output signal. And the mechanism is not hard. You can see that once the PDMS and the your sweat to contact, the triple H3 effect will also result in the electron transfer from the water to the PDMS layer. And then after separate, it will also create a potential difference. So if now there are more ions in water, actually it will neutralize the general triple H charges and decrease the electric output. So now we are trying to move this project for the drug screening. Anyway, but for that one, actually we cannot have the selectivity. That's also the main challenge for the solid and liquid content education. And then in this story, we also collaborate with Professor Dr. Choi and Professor Semin Lee. We just studied the possibility of using the content education, solid and liquid content education, to develop the catching sensor. So we developed the TiO2 nanomaterial and to contact with the liquid. And you can see that the mechanism is still quite similar to the previous results. And the reason why we use the TiO2 nanomaterial is because the catching will spontaneous and selectivity to binding to a TiO2 surface because of the ligand to charge the transfer phenomenon. So we have very clear evidence. You can see that from KPFN result. Once the TiO2 surface is binding with the higher the concentration of the catching, actually it will increase the surface potential. And this is we also use the UPS to further confirm the Wolf function. So you can see that after the binding of the catching, actually this the complex, it has the less the Wolf function, smaller Wolf function. So that means during the contact electrification process, it can result in more the electron to transfer to the liquid. So you can see that from our result, the sensitivity is actually good, like from the 1 nanomolar to the even the 10 micromolar. And no matter you change the contact liquid, I mean that you not only can use the water, but you can also use the acetone. And because of the solid and liquid contact education, it's very durable. So no matter how many times you contact, it's not like the solid and solid the contact. It can provide you a more stable and more reliable output signal. And it will also not affected by the contact frequency as well as the environmental humidity. So anyway, this is a very good comparing to the solid and solid content education. And recently, we also demonstrate it can be used to develop metal ion sensor. So we also made successful to demonstrate for real sample detection. So for this humidity resistant nanogenerator, you can also consider the thermometry the nano sensor. For this sensor, of course, you are not affected by the humidity because the mechanism is based on thermometry. So for this purpose, actually, we have used the titanium nanowire because of it will only react with the mercury ion among so many different metal ions. And after the formation of mercury telluride, its seepage coefficient is much higher than the titanium-based the material. So this is the reason why after the detection of the mercury ion, the output signal will be increased. So we also use the KPFM to get the more detailed information. So you can see that after the formation of mercury telluride, once you can keep higher the temperature, the difference, you can see that the mercury telluride can have much the higher the output than the titanium. And we also evaluate the performance by the changing the environmental temperature, heating the temperature. So you can see that even the temperature difference is small, it can still provide you the sensing the behavior. And the detection limit is good. It can achieve like the 10 nanomolar. So this is already good enough for drinking water detection. And then we also try not only the heating but as well as the cooling. So you can see if in your future application you need cooling the source as your temperature control source, you can see that you can still have the very similar results. And the selectivity and for real sample detection, we also show you a very convincing result. So finally, I would like to thank my students, and recently we collaborate with the many medical doctors in order to help the more the people, especially the patients. And of course, I also want to thank the funding agency from the town government. So thank you.